3. An electrical wire of 2 mm diameter. So let's say this is my electrical wire, 5 meter in length. So this is 5 meter in length, is insulated with a plastic layer of thickness 2 mm and thermal conductivity given. So, and we have to, okay, it is exposed to ambient air at 30 degrees Celsius. So if this is my electrical wire, around it there is, so this is 2 mm diameter. So from here to here, this is 2 mm diameter. And around it there's a plastic insulation of 2 mm thickness. So this is my 2 mm thickness plastic insulation. So the diameter of the plastic insulation is 2 mm, and 2 mm here and 2 mm here, totally 6 mm. So diameter of this plastic insulation is 6 mm. So radius of insulation, let's, if we call it Ri, is 1 mm, and RO, if we call this plastic insulation radius, that's 3 mm. Okay. The outside air temperature is 30 degrees Celsius. So this is my outside air temperature, ambient temperature, and the thermal conductivity of this plastic insulation is also given. For a current of 5 amp and potential drop across 2 volts, so across it there is a electric supply and 5 ampere current is flowing through it. So we have to, the air side heat transfer coefficient, that means basically right here at the surface, because heat is being transported uh, from whatever the heat is generated inside the electrical wire due to the passage of current, goes through this plastic insulation. There is no resistance here, goes insulation, and then it finally goes out to the ambient air. So there is one resistance here, which is, let's call the resistance of the insulation, and there is another resistance here. Let's call that as a convective resistance. That means resistance to convective heat transfer from the surface of the insulation to the ambient air. So for this kind of system, it's very easy. This is the equation which we can write as this one. So this is the overall temperature difference, which is Ts minus T infinity, whereas Ts is the temperature right here. That's what we have to find out. And T infinity is the ambient air temperature. So that's the overall temperature. So Ts is here and T infinity is here. And this is the resistance inside the wire, which is said can be neglected. So this is equal to 0. This is the conductive heat transfer resistance in the insulation. So this is R insulation, and this is the resistance due to convective heat transfer. Let's call it R convective. Okay. All right. So let's write this equation in little more detail here. So what we have here is basically Q dot is equal to this one, resistance to insulation and convective transfer resistance. This is very easy. This is VI, which is 10 watts. And as I said, this is equal to 0. And this is insulation resistance, this is convective heat transfer resistance. So we can write this equation as this one right here, Ts minus T infinity divided by this one and this one. So we have to find out what the value of Ts. T infinity is equal to, we know, 30 degrees Celsius. So the main problem is, this is 10 watts. So main problem is finding out the radius of the convective heat transfer resistance, this one, and the resistance due to the insulation. Now resistance due to the insulation is given here, which is Ro minus Ri divided by the thermal conductivity of the insulation and log mean of the area. Because why log mean? Because as you can see, the area is continuously changing from here to here of the conductive heat transfer resistance. So that's why we have to take the log mean. Okay. RO is 3 mm, RC 1 mm, RI is 1 mm. We have looked into it. Log mean area is equal to area of the surface, which is area of the surface right here. So this area and this area, and we have to take the log mean of that. So area of the surface minus area of the where divided by log mean of the area surface. Now, area of the surface is, of course, area of the where is 2 pi RIL inside one. Area of the surface is 2 pi ROL. So, area of surface minus area of wear is equal to 2 pi L RO minus RI, which is this one, and divided by the natural log of these two surface areas. So, of course, these two cancels out. We get 2 pi L RO minus RI divided by log mean of natural log of RO over RI. So what is the radius of insulation? Radius of insulation is this one, would be equal to RO minus RI divided by this one right here. And of course, there is a K. Now this RO minus RI cancel out. So what we have is natural log of RO over RI divided by 2 pi KL. And if this is calculated properly with the proper unit, this becomes that's the resistance due to the insulation. And convective heat transfer resistance is, we know, is equal to 1 over HO AO. So 1 over HO, this is the area of the uh, plastic insulation that's at the surface, and this is already given. And if we calculate that, that becomes equal to 0.5308 Kelvin per watt. Okay, and this area of the surface is 2 pi LRO. That's a radius of the insulation. So in this equation, we have calculated this one, we have calculated this one, we know what is this, we know what is this, and the surface temperature can be calculated, and the surface temperature comes out to be equal to 38.805 degrees Celsius, and that's my answer, and detailed calculation is shown.